there were several questions, and let me try to share my. Right. So I think there was a question by Enrico about the this number of unknowns compared to the number of equations to in the spin hydro that Kenji described. Maybe we can start from that question. Kenji, are you here? Have you thought about this question?
Yes. But I think that the situation is not really different between the canonical case and the Benioff case, because with that additional the condition, the equation of motion are actually identical. And so the key to solve this question is that actually the constitutive equations are actually the equations for such a spin tensor. And so with those additional equations, I think that the dynamics is fixed.
But sorry, but they still have to be coupled, right? Because the S is present also in the spin tensor, not only in the, also in the energy momentum tensor, not only in the spin tensor, right?
Yes.
So they are coupled, so how?
But coupled, yes, yes, coupled, but what you need is the number of the equations matching to the number of unknowns, right?
Right, so let's list again the equations then. So we have energy momentum, okay, conservation, then?
Then the constitutive equations?
Yeah, yes, but so the additional constraint that you impose to ensure.
Dynamical equation is just a conservation law. Is it correct, Kenji?
Yes, that's exactly.
The Masaru, what did you say?
The dynamical equations in your formalism is just a conservation law and how to say, energy momentum conservation law and total angular momentum conservation law. Is that correct? Even in your formulation?
Yes, what I mean by equation of motion are those are conservation laws. And then obviously
then you have
the equation is less. Yes, so I totally agree. The number of equations is less. But so at the end of the day, what we found was that entropy analysis is reduced to the same result as the canonical one. So this means that the constitutive equations must be derived in the same way, and then the formalism is actually reduced to the identical to yours, because the equation of motions are the same. Huh?
Good. Yeah. Then it means that your dynamical number of the dynamical variable is T0 mu and S mu nu. So you have the 4 plus 6 degrees of freedom, and you have the conservation law. So yeah, it is closed.
But in the conservation law for the total angular momentum, if you use only the orbital angular momentum, which is given by, let's say, xt minus xt, where t is the energy.
Sorry, may I suggest?
Okay, so that constraint. Okay, the identity. So you count it 1, but it is actually 4.
But that, if you don't have the spin tensor, the conservation of angular momentum is given by the conservation of energy momentum.
I understand. But that the identity satisfied by the spin tensor, that is actually not only 1 but actually 4, because that is the 3 tensor with 2 contractions, and so you have 4.
Yes,
right?
exactly.
So
exactly.
in this way, yes, the number matches.
No, but don't we need 2 or more? Sorry, maybe I missed something. Maybe like this without.
Sorry, can I say something? If you don't, can you please share the screen with the equations? Very difficult to follow this discussion otherwise.
So shall I? Wait. So I
you're able to share your screen, I think.
Yes, and I close my presentation. So Okay. Okay, so no. Okay, so the question was that of course the conservation law for the energy momentum tensor that is fine, but the question is the conservation law for the angular momentum. That is in this case not really the independent equations. That is the question, right?
But yes, so if you use the Belinfante, then
Yes. But then you see, so here you have this constraint that is actually the 3 tensor is contracted with 2 derivatives, and so you have actually the constraint from here.
Yeah, right. But those are 4, right? Then we still have 2 equations that we need, right? So we have.
I see. Yes. From the angular momentum, yes, you're right.
Because the angular momentum, if you use the Belinfante, angular momentum.
Sorry, may I have a comment on this? So, of course, using Belinfante formalism, the total angular momentum conservation is automatically satisfied, right?
Yeah, right.
It seems there is no dynamic equation for the S mu nu, right?
Yeah,
I think that is your question, right? So our solution is something like this. So of course we have the conservation equation for the energy momentum tensor and the current, but then when we consider the entropy production rate, that will give us some constraint, something like constraint for the S mu nu, which should be related to some derivative acting on the temperature and the flow velocity. So that actually is that will give us some constraint equations, but that equation is equivalent to the total angular momentum conservation equations in the canonic form. That is what we found.
Okay.
So here's maybe can I say that in this way? So this is a constraint equation which guarantees your equation motion for the energy momentum tensor is not changed. So this is not this constraint equation is not the dynamical equation. So it just guarantees the T mu nu equation motion for T mu nu and theta mu nu is completely the same. So you have the another 6th equation which is for the total angular momentum conservation.
Yeah, but that 6th equation is coming from the entropy production rate. That is my point.
It's coming from the total angular momentum conservation.
It's
Right.
So I say in the canonic form, the total angular moment conservation actually reduced to the some dynamic equation for the S mu nu, right? S mu nu equal to some Q mu phi, something like this, right?
Yes, right.
And actually, that equation it can also appear in our framework by if we consider the entropy production rate. So that means.
But entropy production rate is just another equation which is used to determine what is your constitutive
that's equation will give us some constraint. That constraint is not only one equation, but a set of equations.
What are those?
I think that you need to first fix what is the dynamical equation in your formalism, and I think that firstly you have T mu nu, so you have the conservation law for T mu nu, and you also have the total angular momentum conservation law, and you have the 6 additional equation motion, and you can perform the Belinfante procedure, but the number of the dynamical equation could not change under that redefinitions. So this constraint guarantees that there is no additional another, how to say, equation motion. So you have just 4 plus 6 equation motion, and dynamical variable is beta mu, beta u mu, and S mu nu. So you have 10 degrees of freedom. So it's matched. So there's no problem. So you should not think of this constraint equation as a
If you,
Yeah, dynamic.
sorry,
Yes,
can I
I
say
completely
something?
agree with Masaru. Yes, I'm sorry.
But I think we are
I
talking
agree
about the
with
same
Masaru.
thing.
But no, not the same thing. But I must agree with Masaru. So, this is a very interesting question.
I think, so that's why we actually try to, I mean, try to avoid the Belinfante, because it
Yes,
seems that
yes.
you don't, I mean, you cannot constrain the spin density somehow, the spin potential, or what this has mu nu somehow.
So, but it depends. Sorry, the whole question depends on how many thermodynamic fields you have.
Yeah, exactly. But as
So
far as
if
understood,
you
S
have,
mu is a thermodynamic field, right, Kenji?
no, I mean that the thermodynamic fields are not the conserved currents. Conserved currents such as T mu nu and S mu nu, or sorry, K lambda mu nu, these are conserved currents, but they must be expressed in terms of thermodynamic fields.
Right.
In order to solve the hydrodynamic equations.
Yes.
So how many
Yes.
thermodynamic fields do we have? How many
No,
thermodynamic
so K lambda mu nu identically vanish if you take the divergence. So it is not a dynamical equation. It is just an identity. You do not need to use the equation motion at all to derive
Or
the.
in other words,
Yeah.
Can I finish?
Yeah.
May I finish? What I'm saying is the following: is if you include the spin potential. So if the spin potential differs, so it's some extra thermodynamic fields, which is not identical to the thermal vorticity, then you have 6 additional thermodynamic fields.
Right.
It's like a spin potential. So it's like a chemical potential, but it has 6 components. So if you have 6 more components in your hydrodynamic equations, then you need 6 more equations. And the 6 more equations are provided by the divergence of the spin tensor equal to the antisymmetric part of T mu nu. So you have 6 additional dynamical equations, which allows you to solve, once the initial conditions are given, to solve for the spin potential. Likewise, it's like when you try to solve the mu T mu nu in the usual framework. What your unknown functions are velocity and temperature, right? It's the same thing.
Yeah, this is, I think, is what we are discussing, right?
Exactly. So
are you considering non-equilibrium situation? I think in say local equilibrium, spin tensor has to be proportional to summer vorticity, right?
No, I mean it depends. If you
in local equilibrium, not necessarily. In global,
not necessarily. So in other words, if you include the spin potential, then the angular momentum conservation gives 6 additional dynamical equations. If, on the other hand, you do not introduce a spin potential, then the angular momentum conservation, as it was pointed out by previous, maybe by Masaru, then becomes only constraint on identity. So it is automatically.
Yes, I think this is something very important to really understand, because in usual hydrodynamics, local equilibrium assumption means that given temperature and summer, this fluid velocity, the property of the system is completely fixed, right? And this temperature and the fluid velocities are the parameters in the density matrix locally in equilibrium, right? But now, so now, so this summer vorticity you consider as a like a chemical potential for spin, and once it is given, and if we assume local equilibrium, shouldn't we expect that the spin tensor is also fixed by that Lagrange multiplier, chemical
what
potential,
you said
right?
is correct.
Right. So I don't understand that why the spin tensor is independent of summer vorticity in local equilibrium assumption of hydrodynamics.
This was I think this was the subject of the talk of Enrico, and he may to say argue about this more in detail.
So the
Yeah.
So the thing is that the spin potential the spin potential has to be equal to the thermal vorticity in global equilibrium. A way not
yes, the global equilibrium, I completely understand that. That's really equilibrium. But in the assumption of local equilibrium in hydrodynamics, shouldn't you apply the same feature, at least in ideal limit?
Yeah, that's the problem. For example, so this is something that that we think that, so in local there is no such a thing of local equilibrium when you have spin. So what we somehow found with the kinetic picture is that, okay, this we somehow also arguing, I mean, with Francesco, but the thing is that what makes the collision term vanish, at least in the kinetic theory description that we developed, that's those are the condition of global equilibrium. So there is
you can extend it.
There is no such a thing of
that,
equilibrium with spin as we thought. At least if you start from the kinetic theory, then of course, if you start from Subarev, seems, I mean, there is some debate on that, but it seems that, yeah. So the condition in which the spin tensor is locked to the thermal vorticity, say, so the spin density, the spin potential is locked to the thermal vorticity, are the conditions for global equilibrium. There is no such a thing in local equilibrium when you have spin.
No. You can think of that extension to the local equilibrium, and so you can define the spin potential and the thermal vorticity locally. It now depends on the positions, and when your spin potential is deviated from the thermal vorticity, there is a independent spin mode. So you need to solve the
thermal vorticity is something that is not local by definition because it's derivative.
No, I think we can see this in entropy current analysis. So if you look at right-hand side of divergence of entropy current in canonical form, then we can find this condition.
Yeah.
The entropy production ceases when spin potential goes to thermal vorticity.
Yeah, okay, which is the global equilibrium. It's not the local equilibrium.
No, you can go away from the global equilibrium. So beta mu is a local parameter. So you can take the derivative and you can think it is still the function which depends on the positions. That is allowed in the local equilibrium descriptions. And the problem for the spin density is if you have the local equilibrium, which is characterized by conserved quantity, conserved charge density. In that case, there is no independent spin density. So it is it is completely fixed by the thermal vorticity. But you can think of the some deviation from that situation. Yeah.
I agree, but that's the problem. That if you use Belinfante, we don't have this parameter that shows you how the how the spin potential deviates from the thermal vorticity. So that's why if you have like a system in which the spin relaxation happens with sort of happens slow enough to be somehow considered as a thermodynamic variable, then it seems that the Belinfante doesn't allow you for this. For this freedom, at least what my intuition, my understanding.
Yeah,
this is precisely because
if you go back to the
equations, don't have this enough equation.
And if you go back to the original question, that maybe some confusing point in this slide is there is no equation motion for the spin potential. I think that right, Kenji?
I think means that the third line is the sort of equation of motion, right, Kenji?
No, that is not the equation of motion.
That is for the energy momentum tensor. And so, in fact, the source of the question is not really whether it is a thermal equilibrium or not. But the question is once, so we fix the number of dynamical variables, then obviously the number of independent equations that is different for the canonical and Belinfante, and that is the mystery, right? If the number of the dynamical variables is the same.
Actually, I have quite a formal question concerning this third line, and it's zero provided you can interchange the order of derivatives, and this is true if there is no singularity in the function. And this is, for example, not true for magnetic monopole because of Dirac string. And I wonder, couldn't the transition to symmetric tensor provide some singularity? And but although just is difficult to see.
If you have torsion, then of course, in general, you may have such a singularity. But so in this case, so that is excluded as an assumption.
But I think it's okay.
I wonder, couldn't the transition to symmetric tensor somehow produce a singularity in this function in the brackets in the third line? So
no, but you assume that they are somehow continuous enough that you can take derivatives and all the.
Yeah, but is it really possible to postulate this? And
I think yes. Why not?
Yes, I think so.
Yeah.
I mean, it's just some undetermined tensor. So why would you want it to have it singular? So.
No, I don't want. I am just asking. Although if it would be so, then it would be some partial or just some explanation of the mystery, right? Or no?
Every quantity appearing in this hydrodynamic regime is assumed to be small enough, sorry, smooth enough. Yeah. Otherwise, you cannot apply the hydrodynamics. It will break the derivative assumption of the derivative expansion.
The formal question is whether the transition to symmetric tensor can produce some singularity. And I would say, well, I am aware of and familiar with singularities at infinities, at boundaries. But here it should be rather singularities in the for small coordinates, and this is really, it seems that functions are smooth indeed.
Yeah, I would say that the smoothness for the moment probably is something okay, probably because
So such kind of a singularity appears when you have some indefinite situation, like there's some singularity, vortex, a monopole, or something.
Yeah, exactly. Monopole.
Yes, when you are diagonalize something, but so this is very simple transformation, not really involving any inverse transformation, but this is just adding something, and so that added something can be arbitrarily smooth.
Yeah. Also, just I don't see the reason for such singularity.
Yeah, if you are in the hydrodynamic regime, you should use you should have only such quantity, because if you have the monopole or vortex, as Kenji the first part covers, even if you have the vortex lattice, you should cross-grain the vortex lattice to obtain the hydrodynamic quantity. So every singular behavior is somehow smeared out after the cross-graining. So in that sense, everything appearing in the hydrodynamic equation should be the smooth. Otherwise, you cannot use the hydrodynamics. So the question is whether you are interested in hydrodynamic behavior or more microscopic singular structure or not. So it depends on your resolutions of your problem.
Okay, thanks.
I have a related question. So let me try to share my screen.
Okay.
Kenji, could you?
Yes.
Yeah. Okay. So now I think it works. So I think I have a question about the this sixth component in the hydro description of the spin tensor. But microscopically, every spin tensor seems to have only 3 independent components, right? So in the case of this Pauli Lubansky, we have epsilon mu mu, alpha beta p nu, s alpha beta, and if p nu is 1 0, then only the vector component survives. And also in the case of massless fermion, usually the spin tensor needs additional choice of frame, which is usually is a left frame factor n, and again if n is chosen to be 1, 0, then this has only the spatial component, and there are only three independent components. So now in fluids dynamics description of spin, why do we now suddenly have 6 independent degrees of freedom instead of 3 degrees of freedom?
I think
there is extra constraint like that S mu nu times P nu is 0, right? So that's you. That's really like gauge invariance for photon just cancels time and longitudinal component, right?
This S mu nu.
But this makes it clear why the spin tensor should not be confused with the density of spin of particles.
Yeah. So but then, what is the concept of spin tensor? I mean,
the spin
microscopically,
the spin tensor is a pseudo gauge quantity. Okay, and then it does not necessarily relate to the polarization of particles in a kinetic system. So it's a quantum field theoretical quantity. So the number of independent quantity in hydrodynamics is not fixed by the spin. So that not each component of the spin tensor is an independent quantity. The independent quantities are specified, and the unknown of the hydrodynamics are specified by the thermodynamic fields. When you solve the equation for T mu nu, what you need is constitutive equations, right? You want to know what is the relation between T mu nu and the thermodynamic fields. Otherwise, you cannot solve hydrodynamics. The same thing applies to the spin tensor. The spin tensor is a rank 3 object. It's a rank 3 tensor. So it has many, many independent components, more than 6, okay? It is 6 times 4, so at least 24. However, when you write the hydrodynamic equations, these hydrodynamic equations must be written in terms of some thermodynamic fields. And so which are the thermodynamic fields? The thermodynamic fields depend on whether you introduce this spin potential, which is not locked to thermal vorticity. In this case, you have 6 more.
But
how do
I
you
don't
count
know.
in
Yeah,
so
the
it's not
question
But the
is
spin tensor, so the spin
this is
tensor,
6, right?
the spin tensor has not the
yes.
physical meaning of being the density of spin of particles. Not necessarily. You may introduce spin
But then
tensor.
what is the meaning of n here? So then what is the meaning of S in hydro description? What does it really mean?
I think that the question here is Sij is easy to understand. It usually defines our how to say familiar spin density, and S0i it is I have no physical intuition, and I don't know also I assume that there could be such kind of a quantity in spin tensor, but I don't know whether it is I don't know some theory which could have the S0i because if you consider Dirac fermion system, you can compute the spin current, and what I found what I like have only the spatial component, because S mu nu, sigma mu nu rho, which is a spin current, is shown to be the totally anti-symmetric tensor. So I found that most of the theory could only have the such kind of the totally anti-symmetric spin current with respect to the 3 indices. But I don't know, whether it could be shown from the general point of view. So I don't know whether there's some kind of theory which have the S0i in the some.
When we have the total angular momentum, tensor, we have
yes
G mu nu rho And spin current or spin tensor as mu nu rho is one part of this total angular momentum tensor. So if we integrate,
yeah, that is number of Lorentz generators.
Right.
Yeah.
If we integrate this over a spatial time-like hyperspace, what we get is the generator of the.
Yeah. So what Masaru is saying is that we are not quite sure what the conserved charges associated with the boost generator.
Yeah. Yes. So
that is a kind of
is it really conserved charge? Yeah. Yes.
Yeah, and mathematically it is correct. We could have such kind of the conserved charge density, but
I think the problem is that it involves this kind of a space-time coordinate in its definition. For the boost generator, it involves time explicitly. So how do we actually make some conserved quantity as a quantum mechanical operator if it involves time explicitly?
But
so this is different from, say, this energy, right? This is a really operator, Hamiltonian operator, and we can make statement about conservation of Hamiltonian, but this boost generator seems somewhat special in this respect, I think.
The boost,
usually if we
call it does not commute with H. This is why it is conserved.
I'm sorry?
It is conserved, but
yes, but how do you understand this time, explicit time?
Because it is conserved because H does not commute with J0I. If you write dk over dt, okay?
dk, yeah. Mm-hmm.
If you write this equation, then this is equal to, we have one part is the commutator of H and K, right? Plus, and then you have the derivative of K with respect to T explicit dependence, right? And then you find out that the commutator exactly compensates that, and the result is 0. Yes.
Yeah.
Oh, so,
I agree with that. This quantity is conserved.
Yes.
It is,
so
of
the
course,
K mu
true.
is totally conserved.
Yes, but K mu explicitly depends on time, right? In that sense.
It explicitly depends on time, but it is conserved.
Yes.
Let's see.
But the generators, I mean, we are talking about the generators of the Poincaré group, right?
Yes.
But the generators you have to integrate over the space-time to have the, usual.
I mean, K mu, if the total derivative of K mu with respect to T is 0. So it means that K mu is a constant.
Yeah, I think that is fine. And the question is whether it should be included in Heidel descriptions.
Right.
So you recall that we have the
generator of the
So if you recall the Galilean symmetry, we also have the Galilean boost symmetry. So there should be the conserved charge associated with Galilean symmetry. And as far as I correctly remember, the total conserved charge associated with the Galilean symmetry give us, I forget, the center of mass or center of, how to say, total momentum of the system, or I forgot maybe such kind of quantity. And usually if you specify your frame or your laboratory frame or some convening frame or something, and it is, I think, fixed, and we do not change that quantity. So I don't know whether we should consider boost generator as an independent degrees of freedom in our spin fluid. So that is, I don't know, correct answer.
I think that my impression is that this question of additional degrees of freedom might be related to whether this temperature gradient really affect the spin polarization.
Oh, it does.
Yeah. I think this temperature gradient really precisely this additional 3 degrees of freedom that seems to play a role in the this polarization of lambda. I'm not saying that something is missing, but yeah, this question, I mean, the understanding or meaning of this additional 3 degrees of freedom in relation to spin polarization might be helpful to understand.
Can I say one thing? Maybe it's related to your first question.
I have to leave. Bye-bye.
Okay. Yeah.
Bye,
yes.
Francesco. So you're saying, you're wondering that there are too many degrees of freedom, right? Because you're for this S-mu, right? So I think that in the free case, at least what we get is consistent with what you're saying, because the S-mu nu, I mean, for us, let's say the S-mu nu is the integral of the 0 mu nu component of the spin tensor, let's say something like this. Okay, this is what we call global spin, at least. And this follows this Frankel condition. So what you just said, that something like this, yes. For the free case, at least. So for the, let's say, free case, yes. So it follows the Frankel condition, namely that P mu as this quantity you just wrote multiplied by P mu is 0. Yes. So this implies that what you wrote before, right? That S is epsilon.
Yeah, that's for one particle, right?
Yeah.
That's for one particle, but as a fluid.
Yeah, right.
Shouldn't it be something like this condition, like projection to fluid velocity, something, maybe.
Yeah. So the thing is that if we are, at least in our scheme, if you are away from equilibrium, that's not the case anymore. And you have additional additional terms. I think this is probably, you have to think about that more carefully. But
sorry to interrupt. Is S-mu nu a function of x?
S-mu nu, yeah. Yeah, no, I mean,
it's a function of s.
S-mu nu.
So you probably need to. Yes, but I think when you Fourier transform into moment space, you find something that is more relevant. I think I did it, but I cannot remember what is.
What do you transform? Sorry, I didn't understand.
Transform S-mu nu to the Fourier transform it to the momentum space. Okay. This is essentially like d mu S-mu nu equal to 0. Yeah. If you.
I'm not sure if I follow what you mean.
Do such a transformation, but not this S-mu nu transformed one.
I think we are considering spin tensor in fluid cell. What do you mean by Fourier transform? Are you thinking of some microscopic spin in momentum space?
No, this is not I mean, this is not necessarily an actual momentum space. This is just a Fourier transform. Then, sorry, let me check, because I think I wrote something.
Can I ask? Sorry, may I ask some kind of the practical question to Enrico?
Yeah.
So suppose we have the freeze out hypersurface. So we know what is the configuration of the temperature, fluid velocity, and also spin potential. And what we need to do is we need to translate that hydrodynamic configuration to the particle language. And usually in the context of the heavy ion physics, we use the Cooper-Fry formula, which is used to match that parameter to the particle language, which is defined by the distribution function F.
Yeah.
And if we have the spin potential, especially for the associated with the boost sector, can we have some kind of the effect, or can we translate that part into the particle language?
I would say yes.
If we have the
in the sense that the formula for the let's say, okay, the formula for the are you talking about polarization and Cooper-Fry or anything?
Yeah, I'd like to understand whether we can translate the polarization, the macroscopic polarization, to the particle language through the kinetic descriptions.
Yeah,
so we
yeah.
need to,
Yeah, you can just use the formula that is used now to calculate observable, the one by Francesco and collaborators. But then now you have to consider that the kinetic and or hydrodynamic evolution, whatever you want to, and then you will find some correction to that. Also, yes.
Good. Does it contain the boost sector? So as far as I remember, that your kinetic description, which could have the non-local collision term, only contains the S, 3 vector.
Yeah. Yes.
So it seems that
there is a boost contribution.
Yeah.
Masaru, I think there is a boost contribution. I think let me write the equation of it.
I see.
So if I remember correctly, please correct me if I'm wrong. If I remember correctly, this polarization formula for lambda particle having momentum p is given by this epsilon mu beta p nu and omega alpha beta,
Right.
which is sum of rotisserie.
Yeah, right.
So if p is not in the rest frame, if p is really if p has some spatial component, or 0I component of omega affect the so you have to go to the rest frame of the lambda particle and take spatial component in the rest frame of lambda particle.
So yeah,
and that involves the 0I component of in the left frame of omega too.
Actually, some other way is to use not the angular momentum tensor and vorticity, but use the axial charge. If axial current is calculated, then it's possible to calculate axial charge, whose matrix element are also just related to polarization. And
yeah, because you can prove that this formula that Hong just wrote is, you can also write it in terms of the axial charge, yes.
Exactly.
Vector, sorry, of the axial vector, yes.
And actually, when you calculate axial charge, it's zero component of current. So, and the zero component of polarization appears only if particle is moving, because if particle is at rest, the polarization has just, it was stressed several times, is purely space-like. So if it is moving, so it's also a Lorentz boost there.
Yeah.
So the zero component of S mu nu should be somehow conjugated to the zero component of omega omega 0I, right?
Say it again, sorry, Shumang.
Okay, I mean omega alpha beta is something the chemical potential of S alpha beta. So the spatial component of omega alpha beta is nothing but the somehow like the rotating frequency, so which should be conjugated to the angular momentum. That's the spin.
Yeah.
And it's a time component. Yeah, like what Hong right here is omega 0I, which is the acceleration. So as 0I is conjugate to the acceleration. So the question is, what is this quantity S0I means, right, in hydrodynamics?
Yeah,
In hydrodynamics. Yeah, I think
that's in principle, if the Frankel condition holds, like what we wrote in the top left part, then that's something that you can find from the simply from the rest frame of the particle, and then you boost it.
Yes, for one particle, it seems to work. But what about what p mu we take in the fluid dynamics?
Yeah,
should we take like u mu instead, or?
This is, I think, was done in this Weissenhoff theory. I think they have this u mu s mu condition. Yeah, let's.
In the book called Micropolar Fluid,
yeah,
I recall you know that book. They discussed the classical, I don't remember, maybe classical fluid with fluid cell having inner angular momentum, and also another degree freedom, not only rotating angular momentum, but another, I don't remember. Is that one corresponding to our S0I?
No, I don't think so. Which other angular momentum do they consider? I thought they had only some internal angular momentum, which they call L, which is, for them, is simply
like a spin. That one is like spin.
Yeah, which is rigid body rotation. They have like small particles that they have. The internal angular momentum is written as I omega, where I is the moment of inertia, and omega is some internal vorticity field. Internal
vorticity finally follows from for velocity, right? So
no, they are independent. They are independent because this internal rotation have to be independent.
Well, if you introduce extra independent rotation,
yeah,
yes.
of course, that's all the point. The point of spin hydro is to introduce independent degrees of freedom of angular momentum with respect to the vorticity of the fluid.
Actually, just I already had questions. Maybe it's a bit just different from the general end, but there are some practical examples like liquid crystals, right? Where this is realized in practice and somehow studied. Of course, non-relativistically, right?
Well, there are a lot of contexts in which this has been used. I think also this spintronics, the speaker of the last day.
But this is, I mean, is there spintronics? Well, it's relatively new. I mean, somewhere this this hydro with internal degrees of freedom.
It was
it seems to me that it is liquid crystals or something like that, and where it was already studied, right?
The earliest application, I don't remember, but the theory is from, I think, the 60s or 70s.
Right. It seems to me that it's
long ago, something that sort of well understood in this sense.
Something. But here, of course, it's a new element of just covariance, right? So there are for the right. Okay.
No, but the question of O is something now that I have to think about better, how to really understand whether those are all independent or not.
Is there a global equilibrium for the fluid if it is accelerated?
Yeah, I think so. In general, the global state is not only the rotation, but you can also, you mean relativity, right? Relativistic fluid.
Yeah. Yes.
There is also this other this other state of constant acceleration along the streamlines, so it's not rotating actually. And if I remember correctly, the omega mu, the thermal vorticity, when you write it, doesn't have the rotation term, but only the k term. So if you divide the omega mu in terms of electric and magnetic field, so this sort of decomposition, right? This general decomposition of, for example, we can write omega mu as k mu u nu antisymmetrized plus epsilon u omega.
Mm.
In this case, this constant acceleration solution has only k different from 0, if I remember correctly, and omega is 0. So you have only the components, 3 components, electric-like components, if I remember correctly. So you may have some other state which is not a rotating state of global.
Yeah. So because if we have a global rotation, so we can maintain some spin polarization like Sij.
Yeah.
So which means if we accelerate the fluid, we can maintain some amount of S0I.
But this acceleration.
What is this?
Excuse me. So the I really want to understand what was said by Masaru. So if you express S mu nu in terms of the free Dirac fermion, then so this is a sigma mu nu psi daga psi, and so Masaru said that if you try to express in such a way, S0I is always vanishing. So you said so.
I mean that
Yeah,
good operator
is the axial,
to be there.
the dual of the axial vector, so the 0.
Yeah, and then yes, so the S0I is gamma 0, and the sigma 0I.
You should symmetrize this.
Yeah, it's it's not like this.
Yes, so yes, and so this is a sigma. Huh? No.
Yeah.
The
You should symmetrize this.
Yes, gamma 0 and the the commutator of gamma mu and gamma nu.
No, anti-commutator. This is symmetrize.
So gamma nu is already this commutator.
That is anti-commutator.
Sorry,
commutator.
And anti-commutator with.
This is anti-commutator. And what I said that if you do not anti-symmetrize in this way, that operator is no Hermitian, not Hermitian operator. So it should not be the observable.
Oh, I see.
Yeah. So if you want to define the good quantity, good spin quantity, you should symmetrize this one. So that is by using the gamma matrix formula, this is proportional to the totally anti-symmetric tensor. So that is the reason why. Yeah.
And what is interesting that just because you take anti-commutator of this, there is no projection to gamma mu, and so it's proportional entirely to gamma mu gamma 5, and it is totally antisymmetric. This is indeed the point.
Yeah, this is totally anti-symmetric and dual of the U1 axial current.
And dual to gamma 5. And this is because there are two terms. Only because there are two terms with plus sign. There is no projection to just matrix gamma mu or gamma alpha. There is only projection to gamma alpha, gamma 5, and it is really totally antisymmetric. And it is dual to gamma alpha, gamma 5. So it's related indeed, as you said, to hermeticity, right?
Yeah, exactly.
Yeah, but if this is related to boost, then the violation of hermeticity is actually nothing but the boosting the system, not really rotating. And so what happens if you do this in the Euclidean spacetime? If you
what I'm not completely sure is, okay, suppose that this anti-symmetrized current gives us our spin current. So in that case, this 3 indices, so one index is taken as gamma 0, but if you write the current, so you should have the S mu nu rho, which is anti-symmetric one is gamma mu gamma nu rho. So, and in that case, that current is totally anti-symmetric. So your component is only 4, right? So because
yes.
it is just dual to the your axial current.
Привет. Ну, слушай, пока еще у меня нет такого полного ответа. Значит, то есть Сорин считает, что как бы он все-таки, что должен как бы решать, значит, Кикилидзе. Вот, значит, Кикилидзе там предлагает
Are you speaking Russian?
I'm sorry. Yeah, I think I muted him.
So, Hong, could you share your again share screen? So
maybe,
sorry. So in the
So
whiteboard.
by the way, I didn't want to interrupt this interesting discussion, but I actually realized that my answer to Enrico's original question is sort of trivial. That is 6 equations from the angular momentum conservation that simply relate the anti-symmetric part of energy momentum tensor and the spin tensor. But of course, if you use Beninfante, there is no anti-symmetric part of energy momentum tensor, and so there are less equations, 6 less equations, but 6 less variables, 6 less unknowns, because you have no anti-symmetric part of energy momentum tensor. So actually, the matching is perfect.
Can you re-say this? So the thing is that I understand that since you have to constrain this. So you have to constrain this.
Okay, this in my notation, the theta A is nothing to begin with. And so, of course, there are less equations because there are no such components, right? So if you solve the angular momentum conservation law, then you can get a relation that is the anti-symmetric part of the energy momentum tensor is given by the divergence, blah, blah, of the spin tensor. And so that relation is, of course, unnecessary in the Beninfante because there are no such component, right? So, of course, there are less equations, less components. And so, no problem.
But this is because the Dirac case. If you want to apply this for the gauge field, it doesn't apply because they are totally.
It does. I'm not talking about Dirac case, but this is general case.
No, but the fact that it's totally anti-symmetric is not the case for the gauge field. The canonical spin tensor is not totally anti-symmetric for the photon.
Oh, no, I mean, okay, so of course, the symmetry part and anti-symmetric part. And what I mean is, if you couple the energy momentum tensor conservation and the angular momentum conservation, what you get is anti-symmetric part of energy momentum tensor is given by blah, blah. Okay, and then those are the 6 equations, but in the Beninfante, there are no such anti-symmetric part from the beginning. And so, of course, there are less equations corresponding to less unknowns.
Although this is fine, but how can you go from the canonical formulation to this benefited formulation by using this pseudo gauge transformation to kill these six additional equations? I mean, if you start from the beginning, start with the benefited T mu nu, it's okay. But if you do the transformation from the canonical formalism to the benefited formalism, how this killing of this additional 6 degree freedom happen?
Yeah, because unknowns are just eliminated. And correspondingly, there are less equations. And that's it.
But Kenji has S mu nu in Beninfante gauge only because you
S mu nu is okay. S mu nu is okay. I'm talking about just anti-symmetric part of the energy momentum tensor. That is constrained by angular momentum conservation. But of course, such component is the 0 from the beginning, and so there are no such corresponding equations, and so everything is consistent.
Yeah, I understand start with the gauge from the beginning. But what is the motivation to introduce S mu nu if you start with Beninfante?
Yeah, right. Or on the other way, how do you know what is the pseudo gauge to kill this additional 6, right? You need to first know what S is, then you introduce your pseudo gauge transformation to kill this degree freedom.
So maybe we need to.
No, that is another question. Okay, so I'm just talking about the number of unknowns and the number of equations. And so okay, in this respect, there is no problem. Okay.
But so maybe Enrico is asking in which the situation in which there is a spin potential, so that there should be a degrees of freedom associated with that potential, right?
Also.
Yeah, so if we start with Berin-Fante from the beginning, we don't have any motivation to introduce S mu nu.
Yeah, right.
No, the motivation is different. Right? There is a physical system which could support spin potential or equivalently the spin density. And in order to describe that situation, we need to first specify what is your spin current operator. So at that point, even if you start with a Berin-Fante tensor, you need to, unfortunately, you need to decompose a total angular momentum because you have the spin density in your system, which is deviated from the equilibrium value characterized by thermal vorticity.
I don't understand this.
The thing is that because in the
It's somehow combined with T mu nu, but I mean orbital part in Berin-Fante equation.
So in the case of Berin-Fante, in the original papers, they do something a bit different than at least what we mean by Berin-Fante. So, and this is, I think, what Kenji explained. So they divide the angular momentum tensor into a place which looks like the orbital part with the canonical spin tensor, right? Am I right? Plus a spin tensor, which is something else, which is you can find from the canonical spin tensor, right? It's some derivative of the canonical spin tensor, something like this.